Good morning. This is actually the third of 3 papers on this related topic I've given this year. The others are at the SAUI International Meeting, and that was on weights, engineering of historic ships. And one was 2 weeks ago at the Marine Technology Society, and in that case I talked more about the taphonomy of after the ship is already on the bottom. Well, if you look into the archaeological record, there are remains on Crete that have been dated back to 100,000 years ago. And the only way that humans could have gotten there to leave those remains was some form of watercraft. Now, I think the earliest watercraft that we have any evidence of is about 5,000 years ago. But it's been around a long time. For a very long time, when a ship sailed off into the horizon, most of them, or a lot of them, disappeared, and you know, they sailed off the edge of the map. People had no idea what happened. Around about 1960, George Bass and Peter Throckmorton and a few others started doing underwater archaeology in earnest, and suddenly we could start to see what happened to some degree. But nobody's really ever been able to say, okay, what happened, what caused the various kinds of damage that you find when you do find a ship on the bottom? Oh, how do we, okay. Okay. So, this Navy Marine Forensics Committee, I'm the co-chair, Bill Garski here is the other co-chair. We started looking at this as a scientific discipline. How do you dissect the damage signatures you see on a shipwreck and try to attribute which ones may have happened prior to the sinking? I mean, we know of at least one fishing vessel, the Beth D. Bob, where the owner made a number of changes, including screwing up the heating, screwing up the ventilation in the engine room, so they had to leave it a deck door open, wide open, and they started taking waves, it downflooded and sank. Okay, I mean, sometimes it's inadequate or incorrect maintenance. Sometimes it's fatigue, wave slap or slam, corrosion, biodegradation. What damage that you find on the bottom actually caused the sinking? Well, for something like the Pride of Baltimore, they got knocked down in a white squall so that the hatches went below the waterline and it downflooded and sank very rapidly. There may not be any damage signature due to the sinking because the ship didn't break, it just flooded. Damage due to progressive flooding. Yes, things can get slammed around as water moves around, and especially in storm waves. But we've also seen amazing amounts of damage as the ship's falling through the water column. You can have enclosed bodies that will catastrophically implode with explosive similar to an explosion. The Derbyshire was a 3 or 4 year old gigantic bulker that got into Hurricane Orchid off of Japan. It's metal salad all over the bottom, spread out over 15 square miles. Once it got down a certain amount, this implosion phenomenon happened, and it just shredded the ship. So it's very, you know, you don't always find a perfectly preserved wreck on the bottom. Titanic broke in half. The Edmund Fitzgerald, I presented a paper in 2002 where we did a physics-based. The bow of the ship flooded after the waves reflecting off the back of the house punched in a couple of the forward hatch covers. The bow of the ship flooded. The back of the ship was still buoyant. It was in waves as high as 50 feet. It started flexing. It's sitting on the bottom. The bow is upright, covered in taconite pellets, which was the cargo. The middle 200 feet of the ship is metal salad, just strewn, and then the stern is upside down and on a different course some distance away. So most of that destruction happened between the surface and the bottom. So you get damage and dispersion of artifacts in the water column. And we'll talk about that in considerable detail in a few minutes. Okay, now you've got a ship that's falling through the water column and it slams into the bottom. You've seen car accidents out on the freeway or on city streets. Hopefully you haven't been in one yourself. But there's a lot of crumple damage going on. Okay, now you're going to take something like the Bismarck that we estimate hit the bottom doing 28 knots. Because it was very heavily armored, had very little residual buoyancy, because steel doesn't have a lot of residual buoyancy. It hit the bottom so hard that the bottom the armor belt and the weight of the water coming down at 28 knots crushed the entire bottom up about 1 deck level. It's full of water. Water's incompressible. All the way around the armor belt, the joint to the 1/2-inch bottom plate is blown out. It looked like just somebody took a knife and just peeled it back with a can opener. The only place where it's not is where you had where the turrets fell out, where you already had a large opening for that water pressure jet to exhaust through. James Cameron actually came up with that description, hydraulic outburst phenomenon. Okay, now if you've ever dumped a bag of shock into a swimming pool or dumped lemonade into a clear pitcher, you notice you dump it in the middle and it comes down and it billows out like this at the bottom. And actually, there's a jet of water that forms behind it as it falls. And that continues to impact the bottom for some length of time, very similar to an atmospheric microburst that you get in a hurricane. And that can cause a lot of dispersion of light artifacts, human remains, anything else that's not terribly heavy can get blown out. And then also you get this just because of you disturbing the sediment, you get this enormous mushroom cloud sort of effect of dust and crap and all kinds of other stuff that's blown upwards. Lastly, if you're looking at a ship that went down some length of time ago, you get post-deposition taphonomy, and I'll explain that again quite a bit. All right, so when you start out looking at a historic ship, you got to say what's known, what's unknown, what am I trying to prove? What am I modeling? Well, for some historic ships, it's kind of cool. You know, you go with a ship that hasn't sailed in 1,000 years, and you can take some of these programs and graphically make it sail again, which is, you know, there's no money in it, but it's wicked cool. You can model the sinking. You can model the ship on the bottom being forced by currents and benthic storms, long period swells if the water's shallow enough. The questions are, you know, there's many ways you can approach a model like this, and I tend to go with the easy ones. But this whole paradigm is sort of in its infancy, and I'm sure there's going to be a lot of people trying interesting things going forward. Developing the modeling input parameters is a lot of work, and in this case I've crowdsourced a number of these projects by bringing in either young career professionals or undergraduate students, or in one case we've got going forward a group of high school students. Because while weights engineering on a modern ship has to be done very exactly according to Swibus and such, when you're dealing with a wooden ship built in the 1890s, you're going to do the best you can. And it's a lot of adding things up in a spreadsheet, but it is not rocket surgery, so you can crowdsource some of that sort of work. It can be very time consuming, but so what I've done is I've had these people as co-authors on some of my papers. Normally when we talk about hydrodynamic modeling, the big question is, well, how do you validate and verify it? And the answer is a lot of what we're dealing with here is there's not a lot in the open literature that you can use to verify it. So we can do some amount of model tests, but there's really no money behind this. So it's going to be our best guess and did about like that, and that may be the best answer we can give for a while. Where possible, we're using the best information available, but it's not always possible. So developing the input materials. This is the Newport medieval ship. They were digging a car park or a new car ferry port in Newport, Wales, and they ran into this ship. And it turns out it was put into a dry dock there and then abandoned in the 1400s. And Pat Tanner was able to take the portions in brown here that survived, and using iconography and typical 14th century ship practices, build this as a rhino model and do hydrostatics and stuff like that. I haven't done more than look at that one. You get a lot of different types of information as you go back in history. This is the body plan for the CSS Virginia / USS Merrimack. But it's only available from a hobby, a model maker kind of thing. And when you digitize these and bring them into Excel and start to try to create an input file for the program, there's all kinds of problems where this is more guesstimate than reality. This is the other kind of body plan that you get typically later half of the 19th century, early 20th century. I believe this is the USS San Diego, which was ACR 6, that was either mined or torpedoed. It was the only U.S. ship mined or torpedoed in World War I, and it was off Fire Island, New York. It's a dive destination. Then you get something like this. This is the USS Rhode Island that was towing the Monitor when it sank off of Cape Hatteras. Well, this is about all the information that's available on that ship. I mean, we've got, you look it up on Wikipedia and you can get a length and a beam and stuff like that, but there are no construction details. So how would you begin to model something like that if you wanted to? And there's a whole art form of ways you can do that. One of the things I've found is get as close as you can to a body plan. Build an SHCP model so that you get a displacement versus draft. And that way, when you look at the navigational draft, you get a pretty good idea how much all of this stuff is supposed to weigh. And so then you go through typical, textbooks of the day. ABS was kind enough to give me a copy of the 1921, reissued in 1943, ABS wooden vessel rules. And it's amazing the amount of information that you can put together out of historical sources for something like this. So you can get pretty close, even if you have very little information. Is it going to be perfect? No. Is it going to be a cool project? Hell yeah. So, you do the hydrostatics, you do the writing moments. Writing moments get really interesting when you have these very large protuberances here. And then, okay, the ship went down in a storm. But nobody really recorded data back in 1862 when the Monitor went down, New Year's Eve, 1862. So what do? How do you get data for what the wind and the waves were doing? Well, what I did is I went to the NOAA wave buoy data for that area of the coast and looked at just the month of December and January for all of the 20 or 30 years of data that we have data in existence. And I picked out all the storms that were large storms that had basically the same significant wave height that the historic records say they had, 20-foot waves, that kind of thing. And here's a plot of the significant wave height in meters, and I picked this up and I use that for modeling. Is it perfect? No. It's the best we can get? Yeah. So current versus depth can be very important. Wind speed and direction can be important. All of these things are bound up in very dubious information in the historical record. The wind was blowing at force 5. What the hell does that mean? There was probably 5 different ways of measuring that. It wasn't just Beaufort. And so what it was doing, what the waves were doing, is very, very subjective. So again, you have to make judgments and do the best you can. The metacenter, anybody who's ever worked on submarines or manned submersibles or ROVs knows that the metacenter means nothing once you're submerged. There is no free surface, so you have no metacenter. The stability characteristics are just the difference between the center of buoyancy and center of gravity. However, the dynamic instantaneous orientation also has to include the lift and the drag of all the various components. And so you have to work with Morrison's equation in the time domain to actually get this to work. And I'm not going to show you a bunch of equations. There's very few that I use because I use canned software to do this. This is the midship section of the Lusitania. Notice that very thin metal sections, not a lot of structure in terms of the portion of the volume it takes up. This is a drawing of a typical wooden hull form from the ABS rules that I was telling you about. And the wood takes up a much larger portion of the volume of the ship because it's not a strong material, and there's all kinds of reasons why I won't go into. But when this submerges, it's really pretty easy to figure out the center of buoyancy. It's the same thing as the center of gravity in terms of where the material is. This, it's not so easy to figure out. You actually have to do a lot more calculations here to get the volumes and stuff, and especially when different types of timber are involved. Pine is much less dense than oak. Steel, you can look up in a textbook and nail the number, the value of the density of steel pretty darn close, and it doesn't vary much. If this is oak, there's a plus or minus 20% difference board to board on what the density is at the surface. We don't know what portion of the bottom of the ship is waterlogged because it's been in navigational draft for how many years. we don't know how wood crushes with rapidly increasing hydrostatic pressure. Now, I conjecture that wood is like a bundle of soda straws. Some of the ones at the outer edges of this bundle are going to free flood as the thing free falls. Some of them are going to crush. So you're going to have considerable distortion of the timbers depending on the way the grain runs through them and stuff like that. And again, this would make a wonderful master's or PhD thesis for somebody at a college that has, you know, one of the old 18-inch gun shells that they turned into a pressure chamber. But this data doesn't exist in the open literature. Okay, inertia properties. Well, when you're looking at how something tumbles and falls through the water column, the inertia becomes a big, fat, hairy deal. And, you know, if we're doing normal seakeeping stuff, you say, okay, the roll gyradius is, you know, 25% of the beam, and the pitch gyradius is 30 to 40% of the length. You know, that works pretty well. But what do you do when you got that? Or you got paddle wheels on the sides with big guards, and then you've got a walking beam on top. All of those things start to matter, so you actually have to sit down and calculate the inertia. It turns out that the inertia of that board doesn't mean anything, but the inertia of the center of that, using the parallel axis theorem back to the center of gravity of the ship, means a lot. And that's no surprise to anybody that's done a lot of weights engineering. Okay, lift and drag properties, and this is something that Professor Trosch brought to my attention. Different pieces on a ship have very different Reynolds numbers. So you have to treat them very carefully. You cannot assume that the added mass coefficients and the drag coefficients are all going to be at the same Reynolds number. So you have this kind of iteration with the speed the thing is moving at, and it's also very directional. And so what you wind up doing is you calculate the Reynolds number and the Struhal number and all this, and you give it your best shot. Now, I'm using Orcaflex to model this, and so when I want a rope going, you know, when I want a stay rope going from the top of the mainmast to the tip of the bowsprit, I can put in a 1-inch rope with the right density, with the right drag coefficients, as close as we can guesstimate them, and, you know, it'll even do vortex shedding to some degree. I can put in mast, I can put in smokestacks. It's a lot of work to put in each one of these items independently, but you can do a pretty good job of it. And the bottom of the table is just metric units versus, you know, I wasn't sure. Some people don't speak English units so well. Okay, a typical wooden hulled steamer or something. Well, there's boodles of data for the resistance of a ship going forward. A little bit for it going backwards. Very little, if any, for it going sideways or going straight down or going straight up. So when in doubt, with a complete lack of information, I've got Horner, I've got dozens of other references. I just pick one. It's wrong. I know it's wrong. But again, it's as close as I'm going to get without doing some model tests. The first time I tried this was in 2012, and I did the USS Monitor. Did many months of work recreating the ship in CAD and recreating the whole weight budget and the inertias and everything else, and created this model of it sinking. And I was able to show, this was tricky to set up, show the ship rolling over on the surface, the turret falling off, and then here's the picture of it on the bottom. That's the turret under the end of the ship. And this is the NOAA picture, and here's the turret, and you know the engine space is back here. We're able to get it to land in about the right place, which, you know, when I started this, I had no idea whether it was going to work or not. And it did take a little bit of fooling around with figuring out which part of the ship you were going to start with the flooding where. But we were able to reproduce what we found on the bottom, which was really illuminating. Okay, so I pulled together this kind of generic top-scale schooner. It's not an actual ship. It's just an illustration. It's scaled so that it's about right for a typical top-sail schooner. And I put in some of the lines, and I put in some of the rat lines and the masts and the spars and whatnot. And then I played games with, okay, what happens if I just release it at the surface, and I've set the weight equal to the amount of buoyancy, so I know it's going to sink, or I've set it a certain amount more, and I can set, you can play these games very easily in Orcaflex. And here's what happens if the center of gravity is 1 meter after the center of buoyancy. Notice that because you have all the top hamper at the right drag coefficients and the right drag areas, it actually does kind of a plunge and flutter thing. It does more so if you have in this case, you have the center of gravity forward of the center of buoyancy. And that's, what flooded first. That's a lot of stuff. And I've done this in 2,000 meters of water. The problem with that is it's a little tiny speck that's doing something on the way down. You just can't see it on the screen. You can zoom in and whatnot, but it's harder to see. So I did a short water version here. You can still see some of the patterns. Here's, if you set the weight minus the buoyancy against the drag, and you solve for the vertical terminal velocity, and Orcaflex does that all automatically, you get a number. But because you have this flutter phenomenon, because you have many, many different things, and because they're constantly changing orientation. Now, I mean, on a typical right circular cylinder like a mast or a rope, the drag along that object is 1/100th of the drag across that object. The normal drag is about 1.3 to 1.5, depending on vortex shedding. And the drag along the member is maybe 0.01, 0.07, something like that. So all of this figures in, which is kind of elegant. You can actually, in Orcaflex, turn the rudder at an angle, and it actually makes it twist as it comes down to some degree, to the extent that you have forward motion acting on the rudder. But you can put in lift and drag coefficients for a wing with that aspect ratio and that size, and it does a pretty good job. I haven't tried sails yet. That's going to be an interesting problem. But again, here's the bow. Here's the blue line is it's falling level, and you can see the kind of surge and fall as it's going through the water column. Here's bottom impact. Falling by the stern is the red line, and you can see the motion is quite different. But here's where it impacts. And then if you don't set the bottom stiffness just right, you can set it with different friction coefficients, different impact coefficients. And you can set all kinds of things like that for the ship as well. But if you just take the simple answer, it hits the bottom and it kind of bounces a little bit before it comes to rest. And that's what this is, and it doesn't really mean anything. By the bow, you get the same sort of stuff. And you can see the time that it takes to reach bottom, and even this shallow water depth, depends very much on the orientation where it goes. Same, and of course the terminal velocity determines the impact factors you have to deal with. So the question was, what happens if stuff falls off the ship? Well, how do you define stuff? So I picked some fairly simple objects, carpet bags, steamer trunks, and luckily I had some of those laying around the house. My wife's family never threw anything away, so we have lots of old stuff. I won't call it antique, it's just old. There was cheap stuff back then too. So I did some measurements, put it on a bathroom scale, got some weights. And I said, okay, what happens if I let this stuff free fall? And here it gets kind of interesting, because these were all released at the surface at exactly the same time, and there's an enormous scatter to how far they're carried in the current just because of the terminal velocity. If it falls slower, because it's got a larger area or less weight, it travels much farther. So you get this kind of sorting. A heavy object with smaller drag area falls much faster, and so you get this sorting. If you do something like a Gulf Stream current profile, first it goes north because you're in a 4-knot current at the surface. Then it goes east or west once it's down in the midwater, and then once it gets down near the bottom, it goes south again. So you can actually wind up almost back where you started by the time it reaches the bottom, even though it was traveling north at 4 knots. We played that game in 2002. The Brits unfortunately lost a helicopter out in the Gulf Stream in 4,000 meters of water. And I did this in Excel. I didn't have Orcaflex set up at that point. And just by assuming that it was falling at 1 meter a second through the Gulf Stream current profile that we had available, I predicted a spot on the bottom based on where it left the surface. We were off by 100 meters. In 4,000 meters of water with really sketchy data, I was impressed. That was pretty good. Directional failure of restraints. The Bismarck left the surface upside down and bow last. It hit the C-mount right side up and bow first. All 4 turrets fell out. Turret Bruno, the second one, wound up way down here, but it got hit. It probably wound up pretty much in a line with the other turrets, which are here, and it got smacked by the wreck as it slid past. So we know the Bismarck slid a great distance, like 1,500 meters, down the side of a seamount. What happened is it hit some unconsolidated settlement. We had this hydraulic outburst that probably further liquefied the bed underneath it, and it, tobogganed down until it kind of ran out of momentum. Bottom impact mechanics. When the stern of the Edmund Fitzgerald hit the bottom, it plowed up a big sand dune on one side. And we've seen that on the Titanic and a bunch of other ships. They're not coming in straight when they land, and you can tell a lot sometimes by, the shape of the sand dune and where they're not. This is just taking an Orcaflex simulation and freezing it at the moment of impact where you can see the bow digging in. And if you leave the trails turned on, you can sort of see the slide scar. And we've seen slide scars on, there's a wreck in the Baltic that went down in the 1600s, and the slide scar is still apparent behind it, which is kind of cool. So we've talked about all of these things. We've done free fall studies of taconite pellets independently, anthracite coal falling independently, and then the debris-free items that I talked about. Okay, your ship crams into the bottom, and it's doing some speed. If it's a wooden vessel, maybe it's only going 5 or 10 knots. If it's a steel vessel, it could be doing 20 knots. The metal falls a lot faster. Not a big surprise there. And you have impact damage. Well, we know on some vessels like the Hoyt Vandenberg, which was deliberately sunk for a dive wreck, it hit the bottom bow first, and the bow did significant crumpling on impact. But nobody's ever modeled bottom impact crumpling on a wreck that I'm aware of. And it's something that would be a very difficult thing to model. Look in a textbook, any textbook for the strength of a material. That's based on the lowest 2% of a bunch of ideal coupons that were machined and broken in a tensile machine. If you actually repeat that, you find out that there's a significant amount of scatter. Well, when something actually breaks, you've got stress concentrations, you've got fatigue life used up, you've got any sort of surface imperfections, you've got corrosion. You don't really have any way of coming up with a perfect answer for how strong that was. And then you've got something like a ship structure that's massively statically indeterminate. You would have to do an FEA model. You would have to assume sort of a median value or maximum, pick a value for the strength. If it's a wooden vessel, the strength is very directional, and you don't know where they ended each bolt, each particular timber or board. So it gets pretty tricky. I'm not sure you could ever do more than a qualitative answer to that, but I'd love to try. Taphonomy, from the law of burial. It's used very much in the archaeology context. Ship sitting on the bottom, rocking back and forth in either a benthic storm, or in this case it was 100 meters down and it was 16-meter waves going by, or 10-meter waves, I forget which I ran. But the thing starts rocking back and forth. Now these things are sitting here and they're rotting away and they're waterlogged and there's fish biting them and there's all kinds of stuff going on. And you can see over time this is going to kind of rain down into a debris field. But some of the damage definitely happens on the bottom, and we can't model it perfectly because we don't really know how much it's going to embed itself in the bottom, and then how much velocity it's going to take to re-entrain that stuff. There's a lot of good work done in the sediment transport community that would help with that, but again, that's bringing in a whole nother specialty to look at how the wreck breaks up and moves around. So accuracy, verification, validity. All models are wrong, some models are useful. If you're trying to find out what happened to something like the Titanic, we can reinvent the debris field using this method. And there's some interest in doing so. For modern wrecks, we can look at how different pieces were carried a different distance in the current as between the surface and the bottom. I'm working with one of my young professionals. We're actually going to take the Army and the Navy anthropomorphic indexes for males and females, and we're going to look at human remains using this program. Nothing smelly or icky, but strictly digital. But we can predict how far, a skinny person versus a fat person would fall in different currents, and how they would move downstream, and how the waves move them around and whatnot. And that may be useful to the search and rescue community at some level. Horner actually has some pretty good data for human body mechanics. I know we're probably out of time, but there's a coffee break after this, so if you get up and leave, go ahead. Otherwise, I'll keep gibbering. And I'd like to thank the other members of the Marine Forensics Committee, especially Bill, my mentor, colleague, and friend. And also like to recognize the CSC Distinguished Engineers Program that made it possible to work on this and had paid my way to get here. And other than that, I'm done. But I have a bunch more of the videos if anybody wants to see them.
As Sean mentioned, it is coffee break time, so those who would like to, please feel free. In the meantime, I will offer the audience an opportunity to ask questions.
Because I have a discussion here. Whether reinforcing Sean's points.
All right, I'm just going to loop some of these videos back here. Yes, sir.
I'm interested in the concept of information we might obtain from the debris field, et cetera, towards removal of oil from sunken wrecks. And do you think there's some way to characterize the probability or likelihood of oil still being contained in the wreck based on?
The first time I ever used Orcaflex to do this sort of modeling, I was modeling the PRM, the personnel rescue module of the subsea rescue system, pickling its umbilical and coming up off of a submarine and tumbling on its way to the surface. I think what we would have to do for the case of oil dispersion is we would have to say for a glob this size and model it as a sphere or an oblate prolate spheroid, something like that, give it a buoyancy, give it a density, and subject it to what we think the currents and the waves were. Yes, we could model that coming up and coming off the wreck.
I'm actually more thinking about trying to predict whether the tanks are damaged from the surface.
Oof, I don't know that. You would have to do a strength modeling of the wreck, and you'd have to look at how the condition it was in on the bottom, and then you'd also probably have to sample the oil somehow. I mean, if it's bunker fuel, I don't know in cold water if that'll ever do more than just turn into a block, whether it will solidify. If it's something light, it's probably going to come out over time, but how soon and how well, I don't know. You'd have to really study the geometry and the chemistry and whether there's any biodegradation of the material and whether there's any segregation into lighter and heavier hydrocarbons due to temperature and time. I mean, it could be studied using this, but I couldn't tell you how to begin with. We'd have to go into it to quite some detail. Any other questions? Yes?
Could you use this the same approach? I know you mentioned submarines.
Yes.
For something like the Thresher, could you analyze submarines with the same approach as you're using for the surface vessels?
You'd have to do it in parts. We know the Thresher crushed, and so you would have to model it going down to crush depth. You'd have to assume, based on some of the wreckage on the bottom, how it dissociated into different fragments at that point, and then you could release those at the depth you think that it dissociated at and allow them to free fall. One thing I found doing, I've done quite an extensive modeling of this for a ship I'm still under an NDA on, so I can't go into the details. But what we found is if you have a lot of layers to the current, you wind up getting a scatter on the bottom in terms of what the final position is. It's not a unique answer, and it's because you have this flutter and you have the influence of all the different drag components acting independently. So it's, you can get a probabilistic answer, I think. I don't know that you'll get a deterministic answer.
There's data around, but most of it's classified.
Right.
John, let me, the one thing we, as a committee or panel did back in 1990s, I think it was, attempt to understand how a ship behaves in the passage through the water column was done in a model of the bow of the Titanic in December 1998 at the Naval Warfare Center in Carteret, Maryland. The sponsor of the experiment was the Discovery Channel for a documentary, Answers from the Abyss. A 5-foot model of the bow using the actual dimensions from the Alliance drawing was tested 9 times. Each test was photographed from the point of release to the bottom of the tank.
Okay. I'm sorry, there was other questions? Yes, sir.
How do you establish what currents are at the bottom?
Okay. I began my career at the Woods Hole Oceanographic Institution, doing buoy mooring work for the first 11 years, and I've done a lot of it in 20-odd years since. There is a body of data out there, but a lot of it you have to either have in situ data, which is scarce as hen's teeth. You can use tidal information if it's near the coast in shallow water. For the particular case of interest on the one I can't get into, it was close enough to the Hebble site, which was a high-energy benthic boundary layer experiment that they did back when I first joined Hui in the early 80s, mid-80s. And what they found is that there's these benthic storms. So you have a normal, 10 to 20 centimeters a second at the bottom that's there most of the time, and then suddenly you'll get a knot and a half of current coming through, or 2 knots of current that'll last for 24 hours with all kinds of turbulence and huge clouds of sediment moving around and stuff like that. And then that'll go away, and nobody's modeled or looked at it long enough to know what the return period of these benthic storms are or what causes them. I mean, but there is definitely a dynamic to the bottom boundary layer in deep water. In shallow water, of course, you have tides, you have all sorts, you have rain events that may cause river flows. It's complicated, and you give it your best estimate from the best data you can get your hands on, and there's a detective work process to finding it.
Have you been called upon the airline industry to help you with some of their interactions?
There's nothing inherently different in how you would model an aircraft versus a ship on this. Nobody's asked. As long as you can get lift and drag and weight properties of the body, you can model it here. It doesn't really care what the body is. Thursday night of this coming week, I'm meeting with the curator of paleontology at the Calvert Marine Museum, who did his PhD thesis on the swimming motion of sea lions and seals. And between us, we're going to figure out the flipper motions of a plesiosaur, and we're going to model it in this software because it allows you to do things like paddle wheels turning or propellers turning. You can actually move independent fins with user input lift and drag curves, and you can give it a time. You have to tell it a time series of how you want it to move. But then we have somebody at NRL who published a paper at the MTS thing 2 weeks ago on a very similar body where he was making flapping fins move. So we're going to try and tie that all together. I wish we had a budget. I wish we had funding to do this. It's 100% midnight oil.
Thank you, Sean. It's been a very interesting presentation.
And the other thing is, because there's no real data to validate it, it's hard for anybody to tell you really screwed up and did it wrong.